No.
So we've seen how the dynamical framework that we've established early on, which consisted in pressure gradient being balanced by friction along the estuary and geostrophy across the estuary, how that gets modified in time and in space. In time by different kinds of forcings, and in space by bathymetry across and along the estuary, and also by morphology. You saw that we saw how curvature effects produce centrifugal acceleration. That would cause advective effects to be important. So that modifies the dynamical framework that we had established. So from now on in the class, we're going to sort of talk about selected topics, and we're going to start talking about turbulence and mixing. And this is not a comprehensive treatment of turbulence, but it's just hopefully an overview of what you've already covered, and to put it at some point in the context of estuarine hydrodynamics. But this topic is a big unknown in estuarine physics. Well, I guess in fluid mechanics in general, but we are struggling to understand turbulence and be able to represent it quantitatively and find parametrizations that allow us to solve the equations of motion. So ultimately, that's our main goal. In those terms, in the equations of motion, where we're looking to explain mixing or frictional effects, that's where we need to understand turbulence. Right? So what are those terms, remember, that we need in the equations of motion, the frictional terms? Not so much advection. Advection we can represent with the mean flows, but these terms come from advection, yes. But they're the frictional terms, the ones that we have the stress divergence. So we have parameterized stresses in terms of eddy viscosities. So we'll cover that. So in order to treat turbulent flows, we need to look at the turbulent kinetic energy equation, and also a turbulent flow. But the equation to describe turbulent kinetic energy is obtained by multiplying the momentum equation that we have times the turbulence, times the flow itself. So it's a scalar product. So we're not going to do that. I'm sure you've done that in another class, derive the turbulent kinetic energy equation. In order to do that, you need to define a total flow that has a mean plus a turbulent part. So that we're going to denote the mean part as capital U and the fluctuating part as a lowercase. And the same for a scalar like temperature or salinity or density or any concentration that we can define in terms of a mean plus a turbulent. How does that look like? What does that look like? Well, pretend that this is a record where you have hours, a record of temperature with hours in the x-axis and temperature in the y-axis. And the way you measure it as fast as you can with the instrument that you have, in such a way that you get all the fluctuations. Some of those fluctuations are noise, but some of those fluctuations are turbulent fluctuations, as denoted by the blue line here. Right. So the signal can be represented by a mean component, which is the red line, as represented here, the mean temperature, plus the fluctuations, which would be the deviations from the mean. So all those deviations. So you have positive deviations and negative deviations. So the average in time of the red line is the red line itself. So the average of a mean is the mean itself. The average of the fluctuations, however, the average in time of the fluctuations, if we average all the fluctuations over this span of time, you're going to see that all the positives are balanced by all the negatives, so the average of the fluctuations in time equals 0. However, well, and similarly, the product of the mean times the fluctuations equals 0, because the fluctuations are positive and negative. However, the product of there should be two lower cases here. The product of t prime, again, these should be lower cases, is different from 0. Why is that? Because the product of t prime would make all these negatives become positive. Right? All the negative anomalies, when you multiply it by themselves, will become positive. All the positive anomalies multiplied by themselves will stay positive. So t prime is different from 0. When you multiply the anomalies times themselves, so the anomalies squared, and you average them throughout this period of time, you're going to get something positive, right? A positive quantity. So if we use this representation in the equation of motion, or in the Navier-Stokes equations. The Navier-Stokes equations are for laminar flows, if you remember, that use the viscosity of the fluid. So these are laminar. The Navier-Stokes equations are for laminar flows. For turbulent flows, we take this definition and put them in Navier-Stokes equations. And the only terms that have products of fluctuations are the advective terms. So, and all other terms remain the same. Like, for example, the local acceleration gives us the local acceleration of the mean part plus the acceleration of the fluctuating part. But this part, this 1, 2, 3, is supposed to be an arrow. So this term is 0. So this term becomes that term. Okay. So where the trick arises is in the advective terms. I mentioned it before. So the advective terms with its mean and fluctuating part can be expressed like that. There's the mean and the fluctuating part. All other combinations are equal to 0. And this term combined with the local acceleration becomes the total acceleration. And this term can be written like that, like the product of u prime, u prime. Is that possible? I'll show you why is that possible. Because these terms are u prime du prime plus v prime du prime plus w prime du prime plus the other combination u prime du prime plus u prime dv prime plus u prime dw prime. So the combination of this product equals this. But notice what does this have that you can identify? These three terms look like what? Yeah, those three terms look like the continuity equation. So that equals 0. So this term, which is the same as this one, is equivalent to that. And now, what does this product tell us? This u prime, and u prime, v prime, and u prime, w prime. What do they tell us? Does everybody know what those are the what? The Reynolds stresses, right? Those are the Reynolds stresses. And what do they represent physically? Think of a turbulent flow and think of the fluctuations of u, of the flow u. So remember, our reference frame is over there. It's, the v flow goes in that direction, the u flow goes in this direction. So a fluctuating u would mean that the flow is doing this, right? So u prime is how much the fluctuations here are correlated to the fluctuations here, some distance in front. And the u prime, v prime is how the fluctuations in this direction are related to the fluctuations in that direction. So the flow is doing this, it means that u prime, v prime are strongly correlated. Or if it's doing this even. And the u prime, w prime, it means that if the flow is doing this, it means that the u component and the w component are correlated. So the covariance of u prime, w prime, that's what U prime W prime mean. So in a turbulent flow, U prime W prime is the vertical exchange of horizontal momentum, the stress divergence in the vertical direction, U prime W prime, which is the most energetic. If you think of a turbulent flow, this is probably most energetic than this one or that one or this one, right? Which are those terms. Unfortunately, we couldn't record that. So U prime, V prime, U prime, W prime are the Reynolds stresses. Okay, so keep this in mind because these are the terms in the momentum equation that we struggle with, right? We don't know what these are, or do we? Maybe we are little by little making strides, small strides to know what they are, because we can do now direct numerical simulations and large eddy simulations, as they're called, in which the equations of motion, including the Reynolds stresses, are solved directly. So for that, you need very small time steps. So you can't go very far in time, unfortunately. So in a decade, we'll be able to do it, I think, as the computer power gets us there. That we can resolve very small scales over a long time. I mean, a couple of days, or 3 days, or 4 days. That would be a long time. Because right now we're able to resolve these. Well, maybe we're already. I don't know. So I'm not an expert on that, but we are starting to be able to resolve, at least over short periods of time, the full sets of equations. Now, why is there a problem with these stresses? Why is it that we don't know what they are? Does anybody know? Because we've added variables to our set of equations. Remember our three equations of motion and our continuity equation? Our three equations of motion have U, V, W at pressure, and what else do we have as variables? U, V, W, pressure, density. So we have maybe five variables with 4 equations right there. If we add U prime, V prime, W prime, we're adding 3 more unknowns with the same number of equations. So we can't solve that system unless we add more equations. So the way we do it is we parameterize these Reynolds stresses. Remember how? Well, there are different ways, so we're going to get there. We're going to get there. So in order to be able to see how we can parameterize those Reynolds stresses, let's look at the turbulent kinetic energy equation. So again, it's multiplying the turbulent flow, the equation for turbulent flow, times U. And now we're dropping the primes. So now all the lower cases will mean turbulent quantities in this representation. And the capitals will represent the mean flow. By the mean, I mean perhaps averages over 10 minutes or 5 minutes, whatever period we choose to average over. And turbulence are the turbulence a few seconds, periods of a few seconds. So that's that's what we get by multiplying our momentum equation times a turbulent flow. And the momentum equation including a mean plus a fluctuating part. That is a mean plus a turbulent flow. So we get all this strange-looking equation. Maybe not strange-looking. Maybe you're familiarized with it. Do you know what these terms represent? Let's see if we can see. First of all, the lowercase e sub ij represents a strain rate, and it means how the flow is sheared laterally and vertically also. So that's the strain rate. Remember, it's where the ij is a sum convention. So that left term on the left-hand side of the equation represents the total changes of turbulent kinetic energy. You see why it's turbulent kinetic energy? Why is it turbulent kinetic energy? So kinetic energy equals what? 1/2 of mass times velocity squared. So this is turbulent kinetic energy per unit mass. Remember the lowercase flows that we representing here are turbulent. So that's the total changes of turbulent kinetic energy per unit mass. The next term represents transport of turbulent kinetic energy. It's transport because it has a divergence on the left-hand side. So the gradient of that quantity in parentheses is transport. So this is transport of kinetic energy produced by pressure fluctuations, like waves, right here. And this is by the advection of kinetic energy. And this, notice, has the viscosity of the fluid. So this is the transport of turbulent, of dissipation. I'll explain that in a second. So the next one, which is a very important one, is the production of turbulence by the shear flow, by the mean shear flow. Notice it's the interaction of the Reynolds stresses. The Reynolds stresses are the use of I, use of J. Those are the Reynolds stresses. Multiply times the gradients in the mean flow. And that's called the shear production term. So it's production of turbulence by shears in the flow. How turbulence gets produced because of the shears of the flow. Then we have production of turbulence also by buoyancy. Do we produce turbulence through buoyancy? If we add heat to a water column, what are we doing to the water column? Are we enhancing or hindering turbulence? We're hindering, right? We're causing stratification. But if we add cold air to a water column, if we apply cold air to the water column, we're making it overturn. So we are causing turbulence. So this buoyancy production term can be positive or negative, depending on whether you are adding buoyancy or adding positive buoyancy, that is stratifying the water column, or adding negative buoyancy, that is causing an instability in the water column. And then the last term on the right-hand side is called viscous dissipation. And again, it has a viscosity there. The molecular viscosity of water is how much? What's the molecular viscosity of water? Do you remember? 6. 10 to the minus 6, what?
Meters squared per second.
Meters squared per second. Right? It's important that you include that in your memory drive. And you have the strain rate multiplied times itself. So that's representing, these shears also are representing the frictional dissipation of turbulence caused by the molecules of water when you have shears in the flow. So let's look at each one. So the first term can be represented for the three components of energy like that, just so that we know what so that we remember what the notation, the sub-index notation represents. So the next term is the transport of turbulent kinetic energy, which has a flux divergence form, which is the partial over partial x of j. That's the flux divergence form, and represents a spatial transport of turbulent kinetic energy. So notice the first two terms are transport of turbulence by turbulence itself, that is pressure fluctuations. So this is turbulence caused by waves, and turbulent transport by eddies. So again, think of a river and how the current of the river is transporting eddies. So that would be this term here. So a current transporting an eddy. And then the third term would be a viscous transport. So also the current transporting a viscous effect. All right, and then what term is that? We said shear production. Shear production. So it's the interaction of the Reynolds stresses, as you saw here, These are the Reynolds stresses interacting with the mean shear. So this here is only one of the three components of this shear production term. So it represents a gain of turbulent kinetic energy. This is a term that only produces kinetic energy. Then we have this that's called again buoyancy production. So it represents gain or loss of turbulent kinetic energy, and it depends on the covariance of the vertical flow with the density. So if the flow is in that direction, then you might have negative buoyancy, so production of turbulence. And then we have here what was this term? The dissipation term. Notice again, this is the general way of expressing that term is like that, because this A sub ij, if you remember, is dui dxj plus duj dxi. So the strain rate, 1/2 of the strain rate is what this is. That's where the 4 comes from. So the dissipation rate is given by this expression. Okay, and it always represents a loss of turbulent kinetic energy. All right. So in many applications, this is an assumption that you take. In estuaries, people are using this simplification to try to study turbulence. So what is the balance? What are we assuming here, and what are we neglecting? If we have this. So there's no changes in time and no transport of turbulence. So we're looking at one location in the estuary, and we're assuming that there's no transport of turbulence. So we have the balance between what and what and what. The turbulent kinetic energy balance consists of production of turbulence by buoyancy and by shear. And that turbulence is destroyed by dissipation, which is the epsilon. Can we measure this term? So again, this is a frontier topic, because the challenge is to measure these terms, and people have been trying for maybe 3 decades now. The one that they've measured usually is this one, and maybe they're able to measure this one. A little problematic has been this one, but now with the ADCP we can measure this one. So we're getting there. I'll show you in a minute how. So I asked you before, how can we determine these Reynolds stresses? And well, the Reynolds stresses interacting with the vertical shear produce turbulence by the flow interacting from the bottom. So we have shear production from bottom stress. We have also shear production from the wind stress, right, that causes stress in the surface of the water. So this is the air, this is the water. And we have shear production from internal stresses also. So this would be in the interior of the water column, flows going in opposite directions, so that's a large vertical shear, DUDC, large DUDC here. So there's a flux of momentum from regions of fast flow to regions of slow flow. How can we parameterize the shear production? The shear production only needs the parameterization of the Reynolds stresses, right? In order to be able to determine how large the shear production, turbulent shear production is, we need to determine the shear stresses. And one way that we have been doing, again, traditionally, is through this turbulence closure, as we call it. This is the turbulence closure that allows us to relate turbulent quantities to mean quantities. So the Reynolds stress equals to the vertical shear of the mean flow. And the proportionality constant is given by this coefficient, which is called the eddy viscosity. This is the eddy viscosity. So near the bottom, in order to know what these Reynolds stresses can be, we can assume that near the bottom we can use this expression. This expression is what you've seen it in your fluid mechanics class. That's the law of the wall. So we can assume that the flow decreases logarithmically as we get closer to the bottom. So what we do not know in this expression is this, the roughness length. So this has units of length. And we don't know the friction velocity, right? What is this? This von Karman constant that equals 0.4, right? 0.4? Right. So from this, how can we make the jump from here to the Reynolds stresses? Well, let's see if we can do it. Well, first, in order we can maybe get a feel or an estimate of what the stress, the friction velocity is from this expression. We know that the bottom stress equals the density of the water times the friction velocity, but it also can be parameterized by this expression where C sub B equals
0.00116.
That's for the air-water interface. We're talking about water-bottom interface here.
2.5 to 10 power minus 3.
Right. Okay, so we'll dispel that notion in a moment. But we tend to use the canonical 2.5 times 10 to the minus 3. So it's a bottom drag coefficient. And this reference velocity is a velocity maybe 1 meter away from the bottom. So from this, you can calculate the drag coefficient if you know the friction velocity. But how can you determine the friction velocity? Any idea? If you measure a current profile, like we do with the ADCP, and if you're able to get all the way to the bottom, can you get that friction velocity using the law of the wall? Maybe, right? You'd need to adjust two parameters, these two and these two, and find the best fit between the observations and this law of the wall. So here's an example of how to do that. There are instances in the tidal cycle. So these are profiles at different times. You can see that the numbers up there represent different times. And so these are profiles observed. I think it's in San Francisco Bay. This is from Ralph Cheng, who's at USGS. So the observations are these bubbles here, these circles, small circles. And the law of the wall are the continuous lines. Notice that sometimes the law of the wall fits the profile nicely, at least in part of the water column, but sometimes it doesn't fit it very well. So what the fit is to try to fit the lowermost part of the profile, which is the one that gives us the roughness length scale, Z sub 0, and the U star, the friction velocity. Does anybody have any idea what the range of values that one should expect from Z sub 0? If I tell you 1 meter, what would you say?
Wrong.
Wrong. Small or large? Too large, right? So what would you expect to have? 0.1 meters? 10 centimeters. Yeah, well, maybe. That's a little too large still. Here is what, from those profiles, these are the values that best fitted those profiles with this Z sub 0. So notice the range in the x-axis goes from 10 to the minus 4 meters, so that's 0.1 millimeter, that's 1 millimeter, that's 1 centimeter. So between 0.1 millimeters and 1 centimeter, that would be the Z naught the length scale. And for those range of Z naught, you can obtain the U star, right, from the law of the wall. And from U star, you can calculate the drag coefficient with the reference. If we go back in here, once you get the U star, you measure this U ref, you calculate the U star by best fitting your observations to the law of the wall. So then you can calculate the drag coefficient. Okay, where can you find the canonical 2.5 times 10 to the minus 3 in this plot? Look at the y-axis and give me the value of C naught for the canonical value of 2.5 times 10 to the minus 3. So this is 1 times 10 to, that is 2 times 10 to the minus 3, 3 times 10 to the minus 3. So we go like over here. So maybe here, right? So that's a value of C naught of 2, 3. What is it?
7.5.
No, this is 1 times 10 to the minus 4. 2 times 10 to the minus 4. Am I doing this right? No, this is 9 times 10 to the minus 3. 8 times 10 to the minus 3. So it's 8 times 10 to the minus 3. Right? So this is for that data set. So 8 times 10 to the minus 3 is 0.8 millimeters, almost 1 millimeter for Z naught. But notice the range. The point here of showing this graph is that looking at the range of drag coefficients. So you can get a 4-fold variation in stress for any given velocity, depending on what drag coefficient you use. And so look at those questions posed there by Mona Smith. So why do we care about this? Well, we care because when you do your calculations, at least in your numerical models, you assume that the law of the wall applies near the bed. So, and you use a single value of Z naught for your model, don't you? So that might be a rough assumption. So this is some of the new things that people are starting to come up with, a relationship between flow and roughness, length scale, and drag coefficient, so that we might be able to parameterize. What we're doing with this is we're parameterizing the bottom stress. That is the Reynolds stresses near the bottom, right? This is what we're doing.
So would you do like mini layers with different drag coefficients, like in your model or something? So you're saying like maybe instead of just saying 2.5 times 10 to the negative 3 or whatever, you would have like a layer of 2.5 times negative 3 and then a layer of
something like that, or you can find a relationship between the flow that you have in your model near the bottom and Z naught and CD and C sub D. In other words, a relationship between U and U star, because you can calculate the drag coefficient from U star and U. So the U that your model calculates somehow translated to U star and then to the drag coefficient. So that's a trick that we need to start thinking about when we use the numerical models, that the drag coefficient should probably be spatially variable. Some people are doing that already, I think. Right? Right? Or not? Do you know of anybody? No? So another hot topic.
So the U ref, that's just the velocity at 1 meter, or 1 meter from the bottom? 1 meter from the bottom.
That's usually where the law of the wall starts breaking up in this sub-viscous layer, I think it's called, or viscous sublayer. Viscous sublayer. Okay, so we're making the connection between the Reynolds stresses. We're seeing how we can parameterize, or how we can represent the Reynolds stresses near the bottom. So we use this parameterization. In the water column, we're able now to measure them with ADCP, and the way we do it is as follows. But remember these relationships, that what we're trying to do is to go from, this is what we used before, or what we've been using in numerical models, and this is what we should be using. We can't do it because we're adding variables to the problem, but now we're being able to measure these terms, this U prime, W prime. So from here, we'll be able to go to here and determine the eddy viscosities, and same with salinities, to determine the eddy diffusivities. So with the ADCP, you can measure, instead of measuring in geographic coordinates, that is, instead of seeing your velocities in east, west, and vertical, you measure it in beam coordinates. So in terms of the beam geometry. So what you do is you calculate the variance of beam 3 minus the variance of beam 4, and they divided by this 4 times sine cosine, where the theta is the angle of the transducers, which is 20 degrees for the ADCPs that we've used. That paper describes how you can get from here to there. And also for the other component, you use the other pair of transducers, U1 and U2. So again, if you use beam coordinates rather than geographic coordinates, you're able to measure these Reynolds stresses. And then you can go from there to turbulent kinetic energy production. If you're able to determine that, you're measuring the mean flow, so with the vertical shear of the mean flow, and then multiply times density, you get the turbulent kinetic energy production. Depending on what units you want for the production, you can use density or not. And then if you use this relationship, you can determine the eddy viscosities. So in other words, now we're able to measure the Reynolds stresses, and we're able to compare those estimates of the Reynolds stresses, calculate the eddy viscosities, and compare those eddy viscosities that we're supposedly deriving from measurements to the ones that are predicted from turbulence closures used by models. I don't know, does anybody use turbulence closures in your models? Have you run models that use turbulence closures? Nobody? No? No? Peng has. I think Amy has. No? Yes. Well, anyway, so there are turbulence closures that determine these eddy coefficients as a function of the Richardson number usually, and mixing length scales. But so now with measurements, we're allowed to see how good those turbulence closures are. So here's an example of those measurements of the Reynolds stresses. So we're looking here at a location in the upper Gulf of California, and this comes from a paper by Sosa and co-workers. And we have here distance from the bottom and time. We have 2 days, and we have the 2 components of the Reynolds stresses, the north component of the Reynolds stresses and the east component of the Reynolds stresses. And notice here that we have these positive pulses of Reynolds stresses and negative pulses of Reynolds stresses. So notice that the main orientation of the stresses are in the north direction here. In the east direction, you can see some also. So it's a positive corresponds with negative east, positive north, negative north with positive east corresponds with. And notice how the strongest are near the bottom. So these are bottom stresses. These are Reynolds stresses from the bottom. Notice the order of magnitude here. It's around close to 2 times 10 to the minus 4 meters squared per second squared. Meters squared per second squared. So these are Reynolds stresses. What do you think could be this thing at the surface? Yes. Did you say wind? Yes. So that's wind. Those are stresses caused by the wind from the surface. Notice that what kind of periodicity do we have here? Well, it seems that almost semi-diurnal periodicity in the wind, right? Because we have one day here, we have 2 pulses. We have another day here, 2 pulses. So it looks like wind, but it has semi-diurnal periodicity. Maybe it's wind, maybe it's not. Maybe it's an internal tide. I don't know. But actually, in the paper, they don't comment much about that. They concentrate on the the bottom stresses. Okay, so that's what they would look like, and you can determine Reynolds stresses now. And from that, you go to calculate the turbulent kinetic energy production in watts per cubic meter, and the relation. Remember how to calculate it? How would you calculate that? The Reynolds stresses, you multiply them times the vertical shear, the shear of the mean flow, that is DUDC, the one that you measure with the ADCP, and multiply times density to get those units, watts per cubic meter. So notice that what kind of periodicity you have in this turbulent kinetic energy production. Notice I've indicated with broken lines the hotspots of turbulent kinetic energy production. So this is a logarithmic scale, and we have on the order of 10 to the minus 2 watts per cubic meter. What's the periodicity of the production? Is it diurnal? Semi-diurnal? We have one day here. How many pulses do we have in one day? 4. So it's 4th diurnal. So it occurs. The pulses of high turbulent kinetic energy occurs. Notice this is the tide. Occurs right in the middle of the tide. So how would you interpret that? Peak. There you go. That's it. Did you hear that?
No, say it loud.
Peak velocities occurring during the middle of the tide, the slack, and so, or no height tide, so it's a standing wave.
So these should occur at the times of strongest current, flood or ebb. So the strongest current is apparently occurring at this phase of the tide, that is at still sea level, which would mean a standing wave, standing tidal wave, right? Because the strongest current occurring in the middle of the tide. For a progressive tidal wave, the strongest current should occur at the extreme. So you have the strongest currents occurring here. That means that we have a standing wave there. And very, very well-defined pulses of turbulent kinetic energy. These are nice observations showing this. Notice that here the surface is contaminated, again perhaps by wind. Not contaminated, influenced by wind. Maybe.
So, I'm sorry, can you say that again? Why are the turbulent pulses then at the... So technically the pulses are at when velocity is the weakest.
No.
So
It would be the velocity would be weakest if it was a progressive tide. So we're looking at the sea level. If I tell you that the tide is a standing wave, when would you expect the strongest current? You'd expect it at the largest d-eta dt, at the largest change of sea level, which is the time marked by the vertical lines, vertical block. Does that make sense? All right. So again, with the Reynolds stresses, we can determine the turbulent kinetic energy production, and we can also backtrack and calculate the eddy viscosity, which is what are shown here as a function of time and as a function of the water column depth. Notice here that you have these pulses, not very well defined, but these pulses of high eddy viscosity on the order of 10 to the minus 2. Again, this is the log scale. So on the order of 10 to the minus 2. But here at the surface, those eddy viscosity seem to be larger from the wind. Right? So on average, if you average over time here at the different depths, averaging over time at different depths, you get this profile of eddy viscosity. So you can compare this profile to what your model tells you, your turbulence closure model tells you. Notice that there's very weak down here, and on average, the maximum eddy viscosity is around 3 times 10 to the minus 3, or if you want 4 times 10 to the minus 3 meters squared per second. So that's on average. You have an increase also here at the surface. Does that look in the order of magnitude that you're used to seeing, eddy viscosity? Again, this is average. Over 2 days, you have 4 times 10 to the minus 3 meters squared per second. So the CGS would be 10, right? Yeah, 30 rather. Order 10, that's 30 centimeters squared per second. So it's within the range that you should expect to see. The range that you should expect to see in these units, meters squared per second, would be on average 10 to the minus 5 maybe when you have very weak mixing, to 10 to the minus 2 for strong tidal mixing. That's the order of magnitude of the eddy viscosities. Approximately that. Would you agree with that, Peng? Yeah. Okay. So let's now look at, we've seen how we can determine the shear production. So the shear production can be determined from measurements of current profile measurements, and using the law of the wall to do a parameterization of the bottom stresses. That's if you cannot measure them directly. There are some instruments actually now that allow you to measure a profile all the way to the bottom. They'll give you ADCPs that measure very small beams, so you can get all the way to the bottom. And you can also determine the shear production for the entire water column from measurements with regular ADCPs now. So that has been a great stride forward in the understanding of in the measurement rather of the Reynolds stresses. Now for buoyancy production, you can measure buoyancy production. All you need to do is measure density and vertical velocities at very small scales in the vertical. So that's a trick, measuring the vertical velocities reliably, because as you lower an instrument, the instrument will be moving. So, and the density you can measure reliably in the vertical if you have high enough resolution, spatial resolution. So with very high frequency sampling, you can get the density. Okay, so let's look at two processes that can cause buoyancy production. One through cooling, and one through double diffusion. So with cooling, what you have is a cold air sitting over warmer air would cause what's called deep convection. So that happens in the fall and winter in the open ocean, and it might look something like this. We have depth here. Notice that the scales that we're talking about are much larger than in estuaries, 1,500 meters depth, and we have 300 days, almost a full year of measurements of temperature. So here we have surface temperatures of around 6 degrees and around 3 degrees here. So can anybody describe that picture? What's going on? You have almost a full year of measurements of temperature profile. Did the measurements begin in winter or in summer? Are we talking about tropical latitudes or temperate latitudes, high latitudes? Notice the maximum temperature. The maximum temperature is around 6 degrees, 6 degrees at the 6 degrees Celsius. You fall there, you fall in that water, and you have to get out immediately. So we're talking about high latitude water. So what happens? We started perhaps in the spring or early summer, and you see the thermal stratification. You see these nice pulses of warming here. And then you have a very intense cooling, and you have this deep convection. Notice how the water gets mixed down to 1,000 meters from the cooling. So that mixing is caused by this term here. So it would be negative buoyancy production. But then what happens if you have cold and fresh water here with small heat loss? So if you have cold fresh water over relatively warmer salty water, where would we have a situation like this? Can you think of a place in the world where you have cold water at the surface, cold and fresh water at the surface, and salty water underneath, but salty water that's slightly warmer? Yeah, also high latitudes, right, where you have intense cooling, but high latitudes in an area influenced by fresh water, like in fjords. In a fjord, you can easily see these in the fall and winter. So what happens there? You have this situation. The upper layer, in the upper layer you have low salinity and cooler waters, and in the lower layer you have high salinity and warmer waters. So at this portion of the water, what's going to happen to the temperature when it's in contact with warmer water? It'll get warmer. Just from diffusion. From diffusion, it'll get warmer. So it'll take a while. It'll be a slow process. It'll get warmer. So if it gets warmer than the surrounding water, and it's lower salinity, where should it go? It should shoot up, right? Like that. And the same here. Below the interface, it will get cooler because of the cooler water on top. Through diffusion, it will get cooler, and then it'll shoot down. So that's what's called double diffusion, because at the interface you get double diffusion mixing. How long do you think this go in terms of depth? How far do you think this process can go? That is, this process will go up by how far in terms of depth, do you think? 10 meters, 100 meters, 1,000 meters, 1 meter? 10 meters? That's a good guess. And that's typically the case, around 10 meters. So between 1 and 10 meters. So these excursions are not very long, because immediately they will find, these parcels of water will find their depth of neutral buoyancy. But imagine this going like that. I have a simulation, a lab experiment. It's a very nice experiment. I'll show you. I'll show it to you. So let's go back. So what we have here, I don't know, can you see the screen? Not sure whether. Oh, there it is. So this is a tank in a lab, and you have a stratified water column in salinity. and it's being heated from underneath. So as it's heated from underneath, so this is how you start creating this layer here, and the heat is starting to go up and starting to form these other layers. You see? I'm just going to let it go. So there's the second layer is well formed now, and the third layer is starting to form. And now the third layer is better defined, and the heat's starting to go up to a fourth layer. You see the cells, the small cells, convective cells. And now an interface is starting to form in that upper layer. Here. There's the interface now, better defined, and now there are convective cells here, sort of forming yet another layer. This is centimeters the scale, 5 centimeters. And there's another layer. So see the beautiful layers form. So double diffusion. So at the end you get layers of mixed water separated by an interface. So all these layers have mixed properties. And these are interfaces separating the layers. So you get buoyancy production through this process also. And you may have that in estuaries, like in fjords, as we mentioned. So I'm just going to close today by showing you a couple of examples of layering mixing with data. So these are data from the Arctic, and this is a temperature profile here going from 150 meter to 250 meters. So only 100 meters of the profile, but this follows the trend to the surface. So notice the values. It's minus 1.5 here, 1. These are degrees Celsius. Why is it frozen? Why isn't the water frozen? Pressure at that depth is not that important. How about salinity? Yeah. So salinity is the freezing point decreases as salinity increases. So that's why it's not frozen. So anyway, you see this trend of temperature increasing with depth, and you see in this window that's approximately 20 meters or 15 meters, you see this staircase distribution of the profile. So these are the layers mixed by double diffusion, and look at the interface. So these layers are like 2 or 3 meters deep. So that's through the process of double diffusion. Then in a fjord in Chile, right here, there's the inland sea of Chile. All this is land. And we're looking at this small fjord here. And we're looking at salinity at different times. And you see this staircase distribution of salinity, where you see the layers again are like 2 or 3 meters. So you see it's more or less mixed here, then the interface, then more or less mixed, then the interface. So again, you can have buoyancy production from this double diffusive. And that happens when you have a system with high salinity warm water underneath low salinity cool water. And that has to be in a place where the currents are weak or strong. Weak, because so if the currents are strong, shear production would dominate the mixing rather than this double diffusive layer. Okay, so yeah, we'll stop right there, and we'll start talking about dissipation and how to measure dissipation next time.